Assalamualaikum and hi Dr. Musab and Dr. Liana. My name is INTAN NABILA binti AMDAN together with my groupmates FILZATU HANNANI, SITI NORKHOIRIYAH and SHAN. We are very excited to present our project, the Mixing Time Residence Time and Efficiency Analyzer. Our goal for this project was to take the theoretical maths we learned in class and use it to solve a real practical industrial problem. To begin our presentation, I will be walking you through an overview of the application and its main purposes. What exactly is this analyzer? At its core, it is a robust computational engine wrapped in an interactive MATLAB graphical user interface. The app acts as a digital twin for a continuous stir-tank reactor, or known as CSTR, specifically modeling a fuel blending operation where base gasoline is mixed with a high-octane additive. Instead of relying on static steady-state algebraic equation, our application actively computes transient time-dependent behavior. The interface is designed to take the complex outputs generated by our numerical solvers and translate them into real-time visual curve and actionable data for an operator. While we build this app, we have to look at both the engineering and computational challenges. On the plant floor, operators face a delicate balancing act, run an agitator too fast, and energy costs skyrocket, which is run it too slow, and the fuel mixture fails quality standards. Because these fluids' behavior change over time, it represents a dynamic system governed by complex ordinary differential equations that are difficult to solve analytically. To find the exact, cost-effective sweet spot for the agitator's speed, we realized we needed a tool capable of executing rigorous numerical simulation and multi-objective optimization. The main purpose of our app is to act as a digital troubleshooter that achieves 4 clear project objectives. First, it helps operators achieve the target fuel quality, making sure the final blend is perfect. Second, it minimizes mixing energy to keep electricity bills as low as possible. Third, it reduces additive costs by making sure the factory does not waste expensive chemicals. Finally, it achieves all of this by optimizing the agitator speed, finding the exact RPM needed to balance good mixing with saving.
Next is on numerical methods used. So for our analysis, we applied two numerical techniques, the Range-Kutta fourth order and golden section search. So the Range-Kutta method was used to solve the concentration time relationship in the mixing tank. It gives accurate result for transient behavior until steady state is reached. And the governing equation is shown here. So which is dc over dt equals to q1 times c1 plus q2 times c2 minus q1 minus q2 times c over v. So the government equation, so here it represent how the concentration changes with time based on flow rates and tank volume. And next, the golden section search was used to optimize the process. It helps us minimize the energy and additive usage while maximizing our fuel quality. And the objective of this function combines energy and cost efficiency, and the algorithm finds the best flow rate ratio for optimal mixing performance. So let's focus on mathematical formulation. We have four units that we focus on, where first we have concentration balance, fuel quality, mixing efficiency, and energy model. So first, the concentration balance equation here, which is V dc over dt equals to c1 times c1 q1 times c1 plus q2 times c2 minus q1 plus q2 times c. Over here, this define how octane concentration changes in the tank. And then at steady state, the derivative becomes 0, giving the final concentration here, CSS equal to q1 times c1 plus q2 times c2 over q1 plus q2. And then we will evaluate the fuel quality and mixing efficiency. So quality is 100 minus C final minus C target over C target times 100%. And then for mixing efficiency, 1 minus C target minus C final over C target times 100%. So both are expressed as percentage comparing the final and target octane numbers. And lastly, we have the energy model here, which is E equal to Kn to the power of 3 times T. And K is expressed as Np times density times diameter. So the energy model estimates power consumption using the agitator speed and mixing constant. So for our marine propeller, the power number is 0.3 and the mixing constant depends on the fluid density and impeller diameter. So these equations are the forming the foundation for our numerical simulation and optimization process.
So in the first case, as both inlets flow rate are the same, and then since the additive concentration is higher than the fuel concentration, so the mixture gradually increases from 85 until it approaches the steady state concentration of 97.5. And we can see in the graph here, the concentration rises smoothly without overshooting and stabilizes close to the desired target. And because the agitation is operating at only 500 rpm here, so the power concentration or energy consumption here is relatively low, and the optimization index, because it combines both missing performance and engine efficiency, and since the concentration is very close to the target purity that we set here, so and little energy is consumed, therefore the optimization score becomes 0.97, which is really high. And therefore the system is classified as optimal and the green lantern solve. In this example, we lower the target purity and also we increase the agitation speed. So after we run the simulation, so this will be the result. So in this case, as the concentration profile is almost identical, therefore the final concentration is still around 97. And however, our target purity has been lowered from 95 to 90. And because the final concentration here is 97, which is much higher than 90, therefore actually this creates a concentration overshoot, and the purity calculation is measured on how close the final concentration is to the target value. So since the system overshoot the target, therefore the purity decreases to about 92%. And although the concentration hardly changes, but because we increase the agitation speed from 500 rpm to 2000 rpm, therefore it dramatically increased the energy consumption. And then because just now it is approximately 1.5 million and now it's 28 billion. So this is because power consumption is proportional to the cube of rotational speed. Therefore, when we double the speed, it requires roughly 8 times more power. And although the blending performance is still acceptable, but because of the excessive energy consumption, so this lowers the optimization index to about 0.74, which makes this a moderate performance. Lastly, we will go to the last example where I'm going to lower the fuel flow rate, and I will increase the additive flow rate, and I will remain the others. So this will give a very poor condition is because in this scenario much more additive enters the tank compared to the fuel, where the ratio is fuel is 1 and additive is 50. So since the additive concentration is much higher than the fuel concentration, so the tank concentration will rise much faster. And the concentration, according to this graph, rises quickly and it reaches approximately 107, which is here, the final concentration is around 107. And this is because the additive flow dominates the mixture, therefore, the steady state concentration shift upwards to approximately this value.
And now because the mixture is now far above the required target purity here, so the purity decreases to 80%. And because the agitation speed, we are still remaining it at high speed. Therefore, the energy consumption is still very high. And because of the poor uh, mixing efficiency and also high energy consumption, causing the optimization index to fall to 0.64, where this is above performance. Thank you.
Moving on to the final section of our project, I will show how our MATLAB Engineer Process Dashboard directly facilitates quantifiable advancement in industrial sustainability and planetary health. So as displayed in the interface layout of this image, our software bridges numerical process control with global sustainability metrics. So for the first slides, we will focus on the SDG. So first, the platform actively enforces UN Sustainable Development Goal 7, affordable and clean energy. By utilizing the operating conditions control array, operators can mathematically constrain the agitator speed slider. Because mechanical power scales aggressively as a cubic function of velocity, isolating the lowest viable operational speed through this interface prevents massive unnecessary grid electricity draw. Second, the system aligns directly with SDG 12, which is responsible consumption and production, by cross-referencing real-time mass balances within the feed stream's inputs, specifically balancing the fuel and additive flow rates. The underlying algorithm prevents chemical overshoot. This ensures raw material optimization, eliminating chemical waste and preventing the rejection of off-spec hydrocarbon batches. Thirdly, this operational mitigation leads to a direct carbon footprint reduction. The result panels provides a transparent, real-time output of total cumulative energy consumption. This allows plant technicians to audit operations dynamically and prioritize set points that reduce indirect Scope 2 carbon emissions associated with heavy grid reliance. Finally, the dashboard integrates automated ecosystem and asset protection. The color-coded status lamps and the responsive recommendation diagnostic field function as a real-time process safety interlock. By providing immediate corrective feedback, the software minimizes the risk of volatile chemical venting or hydrodynamic overflows, mitigating toxic contamination of local soil and water tables while simultaneously extending equipment life cycles. In conclusion, this interface demonstrates that transient chemical process troubleshooting can be transitioned from a reactive high-emission paradigm into a proactive low-impact green engineering system. So that's all from my group. Thank you.